Hello, everyone. My name is Antonio Cervantes.
Hello everyone, my name is Avadh Patel.
Hello everyone, my name is Kaiming.
Hi, my name is Venkat Prasanna Kumar.
And we are the buckling team for the ME 273 finite element analysis. So our project focuses on the connecting rod. The connecting rod is one of the most important and critical components employed in the internal combustion engine on any vehicle. Every internal combustion engine requires at least one or more connecting rods, depending on the number of cylinders used in the IC engine. The connecting rod transmits thrust force from the combustion of fuel in the cylinder during the power cycle. That force is then transferred to the crankshaft, which forms the rotational motion to drive the vehicle. It acts as an intermediate link between the piston and the crankshaft, which converts the reciprocating motion of the piston to the rotary motion to the crankshaft. So this means that the connecting rod has both rotary motion as well as reciprocating motion. Since it's subjected to various tensile and compressive loads, it should be designed to have enough strength to withstand high tensile and compressive stresses, and also buckling and fatigue stresses. So to introduce buckling for a connecting rod, the connecting rod is subjected to alternating compressive and tensile forces. Since the compressive forces are much higher than the tensile forces, the cross-section of the connecting rod is designed as a strut. This means that the design should be, it will be subjected to the buckling phenomenon. As shown in the figure, there are two practical buckling modes of the connecting rod. One is called side buckling, which occurs in the direction parallel to the rotating axis on the connecting rod, or in this figure, it's along the y-axis. The other is called front rear buckling, which occurs in the direction perpendicular to the side buckling, or the x-axis. To introduce buckling theory, buckling is the occurrence of instability and deformation in a static structure when an axial load is applied. On a physical level, it's the change in potential energy to kinetic energy. When buckling occurs, it loses its stiffness and thus loses its load-bearing capacity to an extent. And the critical load is typically what's solved for because it is the minimum force to cause buckling. So the different types of buckling that can occur on various parts are the first one being flexural buckling. It's where a member can flex side to side. In the figure on the left side, you can see that there's a structural beam for a building that has flex to the side. The next one is called local buckling, and this is where only a portion of the part has some buckling. Sometimes this is actually sought after because it can help with alleviating stresses throughout the entire part. The third one is called flexural torsional buckling. This is where the member will flex as well as twist. And the last one is called plate buckling. And this is where a thin shell member, such as a plate member on a water tank, begins to buckle due to forces applied to the water tank. So to understand the mathematics behind buckling, let's consider a simple column with the applied axial load P and length L. The Young's modulus is the variable E, and moment of inertia is the variable I. We see here at the top This is the governing equation to this problem, and it's a second order differential equation. It's also can be represented as an eigenvalue problem. To get started on this problem, you have to know the boundary conditions and solve the differential equations. Next, you have to apply the boundary conditions to solve for the constants. From there, you can assume that the values inside the sine function are equal to n pi. And this gives you your critical load as a function of n, where n is your load multiplier, which as you increase n, this solves the equation and increases the buckling load.
For buckling deformation effect, so n is a load multiplier. N's order determine how deform the number. Remember, n equal to 1 gives a minimum crucial load to the buckling in the member. So for the higher order buckling model, if n is greater than 1, it describes a higher buckling model. Because of the literary restraint, the colon will prevent from buckling under the irregular buckling. So the restraint from top allow to hold the colon and stop it from buckling. So the colon can carry more load until it reaches the second buckling load n equal to 2 or n equal to 3. So under the bottom, so when n equal to 1, crucial load equal pi squared times Young's module times inertia divided by length square. And when n equal to 2, so it will be 4 times pi square EI divided by L squared. So n equal to 3 will be 9 times pi square times EI divided by L. So for the buckling shape, it's same. So for n equal to 1, it will be C1 times sine pi times x divided by length. So n equal to 2, Vx will be C1 times sine 2 pi x divided by L. So n equal to 3 will be C1 times sine 3 pi x divided by L. So next slide, I will talk about the buckling end condition. The effective length change based on end condition. So there are 5 cases. So the first case is pin connection on both sides. The second case is fixed on top and bottom. The third case is pin connection on the top and fixed on the bottom. The fourth case is fixed on the bottom and allow move around on the top. The last one will be the translation free and rotation fixed on the top, and rotation and translation fixed on the bottom. So each case will have different effective lengths. Depends on each case, you will use this effective length to calculate the buckling, and there is a K value. And the higher buckling will have higher K value. So next slide will be buckling stress and slenderness ratio. So for the crucial load depends on only 3 parameters. So the Young modulus of the materials and the area moment of cross section and length. It don't need to consider the strength of the materials. So this equation, so on the left, only work for the column that is pinned on at both ends. It can rotate but cannot translate horizontally. So for crucial stress equation, it defines the radius as square root of I divided by A area. The new equation will be right one. So the term EL length divided by R is a slenderness ratio. As you know, the very scanner column will have large slender ratio and the low crucial buckling stress. So then stocky colon will have low slenderness ratio and the high crucial buckling stress. So for the right graph, so the limited, the slenderness region depend on what material using, since the Young's module and the yield strength were affected. Yeah, next thing.
So the assumptions we made for the model is we use two pin joints and the connecting rod, which is connected with the crankshaft. When the force applied in the piston, that is where the combustion takes place in the chamber, the force will act on the piston and the piston will convert, will send the, like the force will act in the connecting rod, and there are two pin joints with the axle load from the piston. So the objective of our study is to find the total stress developed on the connecting rod with the force applied from the piston where the combustion happens from this like when the ignition happens in the piston chamber. If while the force applied to the connecting rod, how much stress it is developed in the connecting rod. And also we are studying the buckling load of the same magnitude when the same power applied at the connecting rod while the power stroke of the spark engine acts. So the methodology we use here is using the SolidWorks. We have sketched the connecting rod. We designed the 3D model of connecting rod using the parameters from a reference paper. And after generating the 3D model, we'll import the model. We will save it as a zip file, and then we imported it to ANSYS. In ANSYS, using ANSYS software, we'll find the total deformation of the model that is connecting rod. Also, the buckling happens in the connecting rod. Using we have set the minimum load and boundary condition that to be applied to find the total deformation in the connecting rod. So the we will calculate the critical buckling stress using the ANSYS software. Normally, we use normally in for manufacturing the connecting rod, they use C708006 material for manufacturing the connecting rod. So here we have used the structural steel material to find the buckling analysis, and we calculated the critical buckling stress using the ANSYS software. And the assumptions we have made for the crank that is connecting rod is we grab the source from GrabCAD, and we use the solid body connecting rod, and it has a realistic geometry. We use the structural steel material to find the total deformation and the critical buckling in the connecting rod.
Yeah, once we have the CAD model available of the connecting rod, we import it into the ANSYS software, and after that we discretized the wall model into the number of small elements. Most of the elements used during the simulation mass was triangular elements. Once we use the adaptive mesh sizing and discretize the wall model into the number of different elements, we found that we have 7,480 elements with 30,823 nodes, and on which we will apply the different boundary conditions, and try to analyze the wall model, and try to analyze that how how the critical buckling stress will changes according to the changes in the load that is applying on the small pinhole. For the next slide, we used the simulation boundary condition. For the simulation boundary condition, we have assumed that the force of 1 Newton is applying downward in the negative direction on the small pinhole. That is due to the shafting that is compressing the connecting rod downward. And for the larger pinhole, we have assumed that that is the fix. So the only boundary condition or load boundary condition for the load, which is the 1 Newton, and which is applying in the negative direction. And this boundary condition will be used, and which it will allow the solver to find the minimum critical load that will cause the buckling to the connecting rod. Uh, for the next slide, uh, once we use these all boundary conditions, and all the once we applied the load and boundary condition, we solver has uh, used 4 modes to analyze wall connecting rod. For that, we can find that for the mode 1, we are finding the load multiplier up to like 24,571, and it caused the buckling, as we can see in the graphical video representation, which is we can find that the only deformation that is taking place is on the small pinhole. But as we are as we are taking more node, and the load multiplier is going to increase, as we can see for the next slide. For the mode 2, the node multiplier for the node 2 is much higher than the previous one, and the deformation that will take place, we can see that in the video representation. Actually, this deformation is taking place along the y-axis, and we can see still there is more deformation on the pinhole side, where we have applied our initial load of 1 Newton. Here we can find some assumption. Here we can find some behavior changes, like as we are going as we are analyzing the mode 1 from mode 1 to mode n, we find that the value of load multiplier is going to increase, uh, as we can see for the mode 3 in the next slide. We finding the load multiplier is much higher than the previous two, and as the load increase, we can find that behavior of the change of shape of the connecting rod. Here we will find here we also find that the deformation which is taking place, in the previous cases deformation was taking place on the pinhole side, but as the load applies, the most of the highest deformation that is taking place is it is on the road that is connecting the small and the larger pinhole. So now the main concentration of stress is we can see is on the road that is connecting, and it is the part which will deform more. As for the mode 4, in the next slide we can find that we are getting much more larger mode load multiplier, and we can see the actual buckling with representation of graphical representation. Here also we can see that the road that is connecting the pinholes are uh, having a maximum stress concentration, and which is having the maximum deformation. Also, the pinhole will be deformed as the load multiplier will increase. So as we are going from mode 1, 2, 3, 4 up to the n, we will find the actual graph that will show the whole scenario uh, for the convergence. So we can see here as we are going from mode 1, 2, 3 up to the end, the forces that are applying on the connecting road will continue to increasing from its previous one, and this is where we can get a brief idea. Once we have a core solution conversation, we can have a brief idea that at what point the connecting road will start to buckle, and what is the part of the connecting road which is getting maximum stress and maximum deformation, which will give us a brief idea about once we that what part are getting more stresses and more deformation, and which will give us the idea about what part during the design, what part uh, we have to make much stronger for to sustain this buckling. All right, thank you.
All right, thank you for watching our presentation.
Thank you for everyone.
Thank you.
Thank you.